Now let's try making theoretical computations and generate our own titration curve. So make sure you have your calculators on hand, some scratch papers and pens or pencils. This will be quite a lengthy video on how we can generate a titration curve from theoretical computations. So we will start by setting our analyte. So let's say our analyte is 25 ml of 0.1 molar acetic acid. And let's set our titrant. Let's use zero point 0.1 molar sodium hydroxide solution. So since we know the formula, MAVA equals MBVB, we can compute for the volume we need, the volume of the titrant that we need to reach the equivalence point. So again, the formula is MAVA equals MBVB. So the molarity of our acid is zero point 0.1 molar. The volume of our acid solution is 25 ml. The molarity of our basic solution is also 0.1 molar. So it follows that the volume of base we need to reach the equivalence point is 25 ml. So now we can start performing several computations. First, we need the initial pH. This is the pH of our analyte before adding any titrant. So this is where we apply the concept of equilibrium. So let's write the dissociation reaction as a guide. The products are acetate and hydronium ion. And this is where we will use the so-called ice table. So we have the initial, change, and equilibrium. So the initial concentration of our acid is 0.1 molar. We are not concerned with the concentration of water. We don't have acetate and hydronium ions yet because this is the point before dissociation takes place. Then dissociation takes place, so the concentration of acetic acid will decrease by a certain value, and the concentration of acetate and hydronium ions will increase by the same value. So at equilibrium, we have 0.1 minus X for acetic acid, X for acetate, and X for hydronium ion. So we will be needing the acid dissociation constant, or Ka, of acetic acid, which is 1.8 times 10 raised to negative 5. And this is equal to products over reactants, right? So we have X squared over 0.1 minus X. So this is just a review. So I'm skipping several or some of the steps. Now we can solve for X. If you notice, you will have a quadratic equation. So you can use the equation solver in your scientific calculators, or you can use the quadratic formula. Solving for X, of course, you will get two roots, right? The first root is 1.33 times 10 raised to negative 3. And the second root that you will get is negative 1.35 times 10 raised to negative 3. So the answer that makes sense is the first one, the positive root. Because if we take this as the one that makes sense, then we will get a negative concentration for acetate and hydronium ions. So we will take this as X. Now, X, as we see here, is the equilibrium concentration of the hydronium ion. So we can now compute for the pH. So pH is negative logarithm of 1.33 times 10 raised to negative 3, and this is equal to 2.88. So let me create a table on this side. So volume of our titrant or sodium hydroxide and pH. So at volume 0, our pH is 2.88. Now, let's say we added 5 ml of our titrant. So let's multiply this volume with the concentration of our titrant, 0.1 molar. 5 ml times zero point 0.1 molar gives us 0.5. This is not mole, but millimole. So in titration computations, it's more convenient to work with millimoles as the unit of amount. So we have zero point 0.5 millimoles of our base. Now we know that we have 25 ml times zero point 0.1 molar of acetic acid. This gives us 2.5 millimoles. This is the initial amount of our acid or the H plus. Well, since this is a weak acid, let's just write acetic acid. Again, we know that there will be a neutralization reaction between acetic acid and your hydroxide ion. So this will produce acetate and water. Now, our limiting reagent in this case is the hydroxide because we only have 0.5 millimole of hydroxide, but we have 2.5 millimole of the acetic acid. So, what will happen is all of this zero point 0.5 millimole of hydroxide ions will neutralize zero point 0.5 millimoles of our acetic acid. In the process, we create zero point 0.5 millimoles of acetate. And now we are not concerned with water because this will just be part of the solvent. So after the neutralization reaction takes place, we are left with 2 millimoles of acetic acid, 0 for the hydroxide ions, and now we have zero point 0.5 millimole of acetate. What do we notice? These are the components of an acetic acid buffer, right? We have the conjugate base and the weak acid. We can actually use the Henderson-Hasselbalch equation to solve for the pH of the system. Because we have the conjugate base, acetate, formed from the neutralization reaction, and we still have remaining acetic acid. So, you know that the pKa is negative logarithm of 1.8 times 10 to the negative 5. That's 4.74 plus logarithm of how do we get the concentration of the base? So we know that we have zero point 0.5 millimole. We divide this by the volume in ml so that we still get molarity. Now the ml is 25 plus 5, the final volume of the solution. So that is 30 ml divided by, we have 2 millimole of acetic acid left in the 30 ml solution. So now the pH is equal to 4.14. So let's write that in our table just to keep track of the pH. So by adding a total of 5 ml, so this doesn't mean that we add 5 ml in one go. So these are just theoretical computations. In the actual experiment, what you do is you add the titrant in little amounts. So if we have added a total of 5 ml, the pH of the solution will be 4.14. Now let's take a few more points before computing for the pH at the equivalence point. So let's say we have added a total of 10 ml of our titrant. Okay, so it's the same process. So we multiply the volume by the concentration of our titrant. This will give us 1 millimole of the base. Again, initially, we have 2.5 millimole of acetic acid, right? So the remaining acetic acid will be 2.5 minus 1 millimole, and that will give us 1.5 millimole of acetic acid. Again, the reaction produces acetate. And we know that the amount of acetate produced is equivalent to the amount of base added to the solution. You have seen that in the table previously shown. So we know that we have 1 millimole of acetate. In essence, all of these 1 millimole hydroxide ions will disappear. So now, again, we have the conjugate base and we have the weak acid. So we can use the Henderson-Hasselbalch equation to compute for the pH at this point of our titration. So we have pH equals 4.74 plus logarithm of 1 millimole divided by 10 plus 25. So that's 35 ml over 1.5 millimole divided by 35 ml. So the pH that you will get is 4.56. Now, notice, let's stop at this point first. Oh, before that, let's write it in our table. So a total of 10 ml of sodium hydroxide is added. The pH is 4.56. Notice the difference between these 2 points. From 5 to 10, so that's a difference of 5 ml of a very strong base, sodium hydroxide. Look at the change in the pH from 4.14 to 4.56. Do you notice something? It's not a drastic change in pH, right? It means at this region or at this region of our titration curve, we are witnessing the buffering action of our weak acid. So later on, if we plot this titration curve, you will see the buffer region. So for now, we are just noticing the pattern or the behavior in numbers. Okay, so let's proceed. Let's say we added a total of 15 ml. So I'm getting another point and then we will proceed to the equivalence point. Let's say 15 ml total of sodium hydroxide solution was added. It's the same process. So you multiply 15 ml by the concentration of our titrant, and this will give you 1.5 millimole of hydroxide. Again, these hydroxide ions will neutralize the same amount of acetic acid. So we have how much of the acetic acid left after neutralization. That's 2.5 minus 1.5. So if you guessed 1 millimole, you are right. And then after the neutralization reaction, so you have 0 millimoles of hydroxide ions and you produce 1.5 millimole of acetate. Again, we have the conjugate base and the weak acid still there present, so we can use the Henderson-Hasselbalch equation. So pH equals 4.74 plus logarithm of 1.5 millimole divided by the total volume, which is now what? 15 ml plus 25. So that's 40 ml. All over 1 millimole divided by 40 ml. So this will give you a value of 4.92. So again, notice, again, our reference is this point, 5 ml to 15 ml. That's a difference of 10 ml of a very strong base. And what's the change in pH? It's still not drastic. 4.14 to 4.92. That's still less than 1 unit. Okay? So again, there's buffering action taking place. So now let's try to compute for the pH at equivalence point. So we determined that we need 25 ml of sodium hydroxide solution to reach the equivalence point. Now this 25 ml of sodium hydroxide solution will give us 2.5 millimoles of hydroxide ions. And this is stoichiometrically equivalent to 2.5 millimoles of acetic acid. This means that all of your acetic acid will be neutralized, right? And what happens is that you form, so all of this will be used up, and in the process, you form 2.5 millimoles of acetate, right? So you have no acetic acid remaining. All of them were neutralized by the base, and then all of them were converted to acetate. So now, what will be, or how will we compute the pH of the system? You know that acetate is also a weak base. This one can undergo hydrolysis. So it can hydrolyze water and it forms acetic acid and hydroxide ions. So we expect that the pH should be basic because the hydrolysis of the acetate produces hydroxide ions. So we need the Kb for this reaction. And we can determine that by dividing the ion product constant of water with the acid dissociation constant of the conjugate acid, acetic acid. So that's 1 times 10 raised to negative 14. This is always, this is a constant. So you should memorize this. Divided by 1.8 times 10 raised to negative 5. And this will give you 5.56 times 10 raised to negative 10. And this is equal to x squared over the concentration of acetate, which is 2.5 millimole divided by the total volume, which is 50 ml. Why is it 50? Kasi 25 ml of sodium hydroxide plus 25 ml of the acetic acid solution, the analyte. So you now have a total of 50 ml minus X. You might be wondering, where did this come from? The ice table. So the X here is the equilibrium concentration of acetic acid and equilibrium concentration of hydroxide ion. So you have the initial concentration of acetate minus the X, right? This is the change. So now you can solve for X. And if you solve for X, now the thing here is that notice the KB is a very, very small value. You can simplify the solution for this one. Since the KB is very, very small, it means the extent of this dissociation or hydrolysis is very, very small. That's a principle in equilibrium. It means that the change, the X, the value of X is very, very small. So this one is very, very small such that we say that this minus X is negligible. The value that you will get is still very close to this 2.5 divided by 50. So we can disregard this, and what you are left with is x squared equals, if you cross multiply this, so you just get the square root. You don't have to solve for a quadratic equation. So solving for x, this will give you a value of 5.27 times 10 raised to negative 6. But again, this is the concentration of your OH minus. Okay, so if we get the negative logarithm of this, that's your POH. And this value is 5.28. So we get the pH. How? That's 14 minus 5.28 or 8.72. So in our table at equivalence point, the pH is 8.72. Now let's try computing for the pH beyond the equivalence point. So again, we reach equivalence point if we added 25 ml of the sodium hydroxide solution. So let's try computing for the pH if we added a total of 30 ml of sodium hydroxide solution. Now the thing here is, in theoretical computations for a titration curve, beyond the equivalence point, the basis for the pH is the remaining hydroxide ions. So what do I mean by that? So if we have added a total of 30 ml of the sodium hydroxide solution, then how many millimoles of hydroxide ions do we have? We have 3 millimoles, right? Again, initially we have 25 ml times zero point 0.1 molar acetic acid. That means initially we have 2.5 millimoles of acetic acid. Now we see that 2.5 millimoles of hydroxide ions will neutralize this amount of acetic acid. And you will be left with zero point 0.5 millimole of hydroxide ion. So this amount of hydroxide ion, or what we call the excess hydroxide ions, will determine the pH of the solution. So first, we will get POH. So that's negative logarithm, the concentration of the hydroxide ions, which is zero point 0.5 millimole divided by 55 ml. So where did 55 ml come from? That's 25 ml, the volume of the analyte, plus the total volume of titrant added. So POH is 2.04. That's the POH. which means the pH is 11.96. So let's write that down in our table. So a total of 30 ml of titrant gives a solution with pH 11.96. So now we are ready to plot our titration curve. We have our volume pH data obtained from our theoretical calculations. So let's create a rough plot of our titration curve. So again, in the x-axis, you have the volume of your hydroxide solution. You can even indicate the concentration of your titrant. And then on the y-axis, you have the pH. So let's mark our volume. So this is 5, 10, 15, 20, 25, 30. And then let's mark our pH values. So let's say this is, okay, that's 7, 6, 5, 4, 3, 2, 1. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, let's plot the points. So at 0 ml, we have 2.88. It's around here. At 5 ml, we have 4.14. That's 1, 2, 3, 4.14. At 10, we have 4.56. At 15, we have 4.92. At 25, we have 8.72. That's around here. And at 30 ml, we have 11.96. So 7, 8, 9, 10, 11, 12. It's around here. There. And now we can connect our titration curve. Okay. So, if you notice, I followed a certain shape. It's because, again, I mentioned that titration curves have distinct shape. So, this is what we describe as a sigmoidal curve. So, you have inflection points there, right? And if you notice, I highlighted the buffering region part here, right? That's from 5 to 15 ml because the pH did not change drastically. So you have your buffer region around here. So if you notice, even with addition of a large amount of your strong base, the pH relatively stays in the 4, pH equals 4 region, between 4 and 5 before you experience a very drastic change in pH right over here around your equivalence point. So in a titration curve, if you see this very steep change in pH, that's a hint that it's an equivalence point. And then after your equivalence point, again, the remaining base, the remaining hydroxide ions will be the one that will dictate the pH of your system.